that not hurt us? They're light, right? They are very, very, very light. So let's just review what they were just talking about. That wasn't a bad Khan Academy video, I thought. It's one of the few I like to show. Okay, so let's talk about Maxwell-Boltzman. Maxwell-Boltzman distribution. The Maxwell-Boltzman distribution. So we started out with a beaker with some particles, right? A thermometer, and this was what? Did you say it was 300 Kelvin? Yes? And we know that temperature is equal to the average kinetic energy of a substance. So the higher the temperature, the higher the average kinetic energy of a substance is. We also know that kinetic energy is what equation? Anybody remember this from physics or freshman? What does Ke equal? 0.5 mv squared. 0.5 mv squared. So, kinetic energy of a nitrogen particle has a lot of velocity, but it has basically zero what? Zero mass. That's why it hits you at 420 meters per second and it does not hurt. You're actually being hit right now by particles. I know. You guys are so strong. Yeah, you're very brave. You're very brave. So, here is beaker A. I'm only going to draw 6 particles because I'm not going to draw 10. So here's 1, 2, 3, 4, 5, 6. Why does that look like cheese?
It does.
Does it?
Yeah.
Like Swiss cheese, kind of?
Yeah.
Or SpongeBob.
Okay.
I could turn that into SpongeBob right now. I heard it was a major disappointment.
What? I don't know who you heard that from. So good.
I did see the Wendy's drive-thru where they like turned the whole Wendy's drive-thru into Bikini Bottom. Yeah, it looked awesome. It wasn't around here
What's the?
because it's the collab. I don't know.
Just don't get the.
Have you seen the Burger King? The product was so good.
I saw they're redoing Burger King.
No, I saw the.
I was told I turned it into Chick-fil-A.
Yeah,
Just
so
saying.
bad.
That's not true.
I was told it was Chick-fil-A.
No, it was bad.
That would blow my mind.
It's gross. It's nasty.
I've heard that's the whole thing.
All right, beaker A. This is at 300 Kelvin. So let's draw some lines. Let's draw some lines. So here is the speed of these particles. Beaker B. Beaker B, this one is going to be 6 more particles. 2, 3, 4, 5, 6. This one's going to be at 200 Kelvin. So my arrows, on average, have to be shorter on beaker B. Does that make sense? Yes? So beaker B, my arrows need to be shorter than my beaker A arrows. Beaker C, if I make this one 400 Kelvin, so 1, 2, 3, 4, 5, 6, these arrows need to be what compared to beaker A? Longer. Watch this madness. Oh, snap. I just bounced that one off the side of the container.
Oh.
Yeah, these are going nuts. But I have a little short one right there. But for the majority, these are, on average, longer. That's one of my better drawings, I have to say. Like, I feel like that's very 3D. Doesn't look like cheese. I told you what I was doing for dinner last night, right?
How was it?
I did it. I had a tummy ache and it felt like my belly was full of lead while line judging. It was worth it. Yeah. And now people are bringing me pizza pretty much all day today. It's a great day.
Dude, if you don't want it,
Yeah, if you don't want to pizza.
let
No, I want it.
I will take out your hands.
I want it.
No, just like Chipotle and Baja Blast in itself is like such a good problem.
Oh yeah, but then nacho fries?
Oh, nacho fries. Love nacho fries.
Nacho fries are so good. Okay, so we got a graph. We got a graph right here. We've got number of molecules, and you guys kind of got this on the video, and we have speed. So this is what you guys are going to have to do on a test or quiz. Couldn't you see this being a really good AP Classroom multiple choice question?
Yes.
Yes. So here is beaker A. Here's what beaker A looks like. This is beaker A. Oh, I hate that I drew the A under there, but that's fine. Beaker B is at a lower temperature. So we know that the peak, and Grady was kind of getting this, right? The peak has to be farther over here, but it's higher. It is higher. Why is Beaker B higher? It's the same amount of molecules, right? So if I am pushing it against the side, they have to go where? They got to go up. Because the area for B should be the same as the area for A. Head nod if that makes sense.
So
Yes.
if this was like an actual like legitimate graph where it went to like 0 Kelvin, wouldn't it just be that all A, B, and C will be the same shape? Because it has enough room to spread out, right?
If they were all the same temperature.
No, I mean like, because if you think about it, like, it can't be skewed because it has the room to spread out and the distribution is the same for each one.
I'm confused by what you're saying.
Like, Henry, do you know what I'm saying? He took stats.
I know what you're saying, but it doesn't really make sense.
Okay, if you go to 0, okay, we can't start a graph, like, if it's like a legitimate graph, you can't start it, because this would be starting at like not 0, right?
I mean, yeah,
Yeah.
no but there's also 0 particles, that absolute 0.
Yeah, but I'm saying if you went down to 0, wouldn't the shape of A here, wouldn't all of them be the same? Because the
Sure.
distribution- That's just making sure like.
At 0, the shape is going to be flat. It's going to be 0 for all of them. But we're not looking at 0. We more care about where is the hump and is it higher or lower?
It would still peak earlier.
Grady.
Is the graph going to be like
An M?
Yeah.
Oh, we're gonna see that later.
There's a lot of like particles that are moving slow.
We're gonna see that later. Okay. Then graph C. Graph C, the peak has to be what? Farther to the right and lower. All right, so here is graph C. Farther to the right and lower. So this way, they have to be more spread out because it's the same area. So just so we have it documented, my question is, why is peak B higher? How would you guys answer that?
Because there's less room for particles to spread out.
Same number of molecules, first, I would say. Same number of molecules, but a higher what? Can I say proportion? A higher proportion at a lower speed. At a lower speed. And we know that our surface area has to be constant. I'm going to change pens because this pen is leaking all over everywhere. So that's Maxwell Boltzman. Got it? We're going to do a little bit more of that in a second. Can I flip my page? Yes, I will.
Surface area equals what?
Constant. Surface area equals constant. Guys, this has been a good quarter. If you think about it, we only have 2 quarters essentially of new information left.
So I was looking. and
Because by-
we've already done, we're doing like 20 labs, we've already done 9.
Yeah. But if you think about it, we've done 9 labs in 9 weeks. If you think about it, we really want to finish all of our new information by the end of the 3rd quarter, which is around spring break, because we need time to review for the test.
So how many will we have done by Christmas?
Yeah.
By Christmas?
Yeah.
How many more labs?
Like,
I don't know, at least 2 or 3 more.
only 2.
I don't know. It just kind of depends.
Wait, so it's the start of the year, just like a lot of labs?
Yeah.
Okay.
Yeah. We have a lab next Tuesday, I think?
The back one.
Yeah, it's a good one. Can I flip my page now? Okay, so let's just quick make sure that we have all of our gas laws down. The one that we didn't talk about yesterday, and you may see this in the book when you're doing book problems over the weekend, right?
I already started on.
Good. Dalton's law of partial pressures. This is going to blow your mind. So Dalton's law of partial pressures says the following. Are you guys ready for this?
Ready? Yeah.
Pressure total. The total pressure of a system needs to equal pressure 1 plus pressure 2 plus pressure 3, ... What Dalton's law of partial pressures essentially says, all of the partial pressures have to add up to the total.
Wow.
Mind blown.
It's
I know.
It's getting
I know.
the same.
This guy got-
It's getting harder every day, all right?
This guy's getting recognition for saying that.
Dalton got recognition for coming up with this. This is the same Dalton. So he comes up with something great, and then he's just like, what about this? Let me name this too. It's like, okay, 2 + 2 = 4. We get it. Let's not do what that is. Okay.
Probably like groundbreaking at the time though.
I mean,
He was just trying to get more.
probably. I mean, back in that time, they thought that like air was an element. So
You should come up with Heller's
Heller's principle.
Air is an element. Land, water, earth.
That's what they thought were the elements, though. What you just said, they thought were the
What
elements.
are those then?
Grady, that's not like
Mixtures, compounds. Yeah.
these are elements.
Okay. So if we go back to the lab, I just want to discuss yesterday's lab a little bit more and make sure we got this. First lab we did looked like this. We had pressure, we had volume, which was a what type of relationship? Inverse relationship. Inverse relationship. If I wanted to make that a direct relationship, how could I graph that? I could put P, and then what could I put down here to make this direct? How can I make it look like this? 1 over V. I'm going to keep the same variables. I should have said that. 1 over V. I could have 2 points here, and I could have M1, and I could have M2. Yes? If I wanted to calculate the slope of that line, we know that y equals what? For slope. Mx plus b? Yes? Y equals mx plus b. And the b on this one, my y should have equaled mx plus what? Should have been 0. Should have been 0. So that means if I am doing m1, m1 would equal what? It would equal y over x. Agreed? And if I'm using my y and x here, that means that m1 is equal to p1 over 1 over v1. You guys with me so far? Yes? p1, because it's going to be change in y over change in x. Yes? p1 divided by 1 over v1. Yes? Which has to equal m2, which is going to equal p2 over 1 over v2. Yes? Which means m1 technically equals p1 v1, and that's equal to m2, which is equal to p2 v2. This is how you would have derived Boyle's law, just from slope. So Boyle's law, we know, is pressure 1, volume 1 equals pressure 2 times volume 2. That was our first one that we did in lab 2 days ago. Next lab. We then had pressure and temperature, which was a direct relationship. Yes? So once again, I have slope here at m1 and I have slope here at m2. We know that y equals mx plus b. B is 0. Agreed? So that means that m1 is going to equal y over x, which in this situation is going to equal what? P over P1 over T1. Agreed? Grady?
Yeah.
You're the one who said change in y over change in x. That's all I'm doing, yes?
Yeah.
Y, x. Yes? Which has to equal m2. Why does m1 and m2 have to be equal? Because this slope is it's a straight line, yes? So m2 has to equal p2 over t2. So if m1 equals m2, then we know Gay-Lussac said that p1 over t1 equals p2 over t2. That was lab number 2. Lab number 2. We good? Because I got to flip my page. Because I'm writing real big. I don't know why. I feel like I took a whole page for what should have taken a third. How much did that take up on yours?
I still have room for the last one.
Yeah. Those are good looking notes. Like, I feel like the notes I give are good.
Yeah, they are.
Like in general. Yeah, I appreciate that. I appreciate that. Okay, I'm gonna flip the page. Third lab we did was what? Volume and temperature? So on this lab, I had volume and temperature. Do I have to keep deriving this? You guys got it, right? Yeah. Yes. Which was Charles' law. I just wanted to show you how these were come up with. V1 over T1 equals V2 over T2. That was the third lab. And then the fourth lab, remember how we took our syringe and we pushed more particles in? Yes? That was pressure and number of moles of particles. That's P over N. Also a direct relationship. Anybody know the name of this law? Who talks about particles? Not yet. Not yet. Avogadro's law. This would be Avogadro's law, because we know that there is Avogadro's number, which is P1 over N1 equals P2 over N2. That is Avogadro's law. I always kind of debate, do I want that to work or do I not want that to work? Because like I want to hear announcements, but that's so loud. I don't know. Like they could turn that, can they turn that down?
Yeah, they like change the volume of it every day.
I don't know. No, I think it just doesn't work some days.
Can they redo the entire
Yeah, it's bad. Yesterday, at the end of the lab, we said that K is equal to P times V. We said that K is equal to P over T. We said that K is equal to V over T. We also said that K is equal to P over N. And we derived this together by combining this and saying that K equals P times V over N times T. Yes?
Yes.
So this K is equal to a constant, which is R, which is equal to 0.08206 liters times atmospheres over moles times Kelvin. You must know this number. You are going to get so tired of writing that number on your homework, you're going to be just annoyed. And you got to put the units there too. And where does this R turn into? This turns into the ideal gas law. And the ideal gas law is PV equals nRT. Pressure must be in what unit? Atmospheres. Volume must be in what unit? Liters. N is my what? Moles. R is my constant, so T has to be in Kelvin. T has to be in Kelvin. So that is the ideal gas law. Every year on the AP Chem test I have taught, there is always one of these. Super easy. PV equals nRT. You will use this on the AP test. I can pretty much guarantee it. Pretty much guarantee it. Which is nice, because it's easy. But guess what they give you your temperature in? Just because. All right, just because. The last law we haven't talked about is P1 V1 over T1. Somebody mentioned this. Is P2 V2 over T2. And that is which law? Combined gas law. That is the combined gas law. So those are all of your gas laws. Okay. Take one of these. Take one of these. So this is a little bit more on this. So that's all of our paper notes. We're going to work through this together. And we're going to call it a quarter. We're going to call it a quarter. Here we go. Is there an extra out there? How many are there? I don't know if I have one to write on. Any extras? Oh, this is the extra. Do you have one, Ava?
I got one.
Oh, perfect. Great. Are you wearing a stocking cap tonight?
A what?
A stocking cap, like a winter hat.
Is that the thing?
What?
No,
Or do you mean just like because it's cold?
Yeah.
Oh,
What do you? You're not?
I don't think so.
I think they're gonna bring a hat and
I haven't
gloves.
planned out my outfit yet.
Because a high of 59 today, and that's gonna be like at 2 o'clock.
Yeah.
It could get down to the 40s tonight. By the 7th inning,
It was 33 when I woke up.
it was chilly.
Who do we have pitching?
We have,
I think we can throw Bybee.
no, it's not Bybee. It's, that's bugging me. Cade, it's Cade.
Smith.
Is it Cade Smith? Hold on, let me check.
I don't think I could sit there for a whole game and watch the pitchers without like.
Yes,
I think I witnessed the first ice of the season.
really?
The puddle in my driveway had a tiny bit of ice on the corners.
Matthew Boyd, which I'm excited about that. That's a good matchup for us. Matthew Boyd.
And we still have Clausen.
Oh yeah, Clase's, he's ready for 2 innings tonight.
He hasn't pitched yet this season, right?
We haven't needed him. We haven't been in the same situation. We've been losing. Yeah. Okay. So this starts out with talking about the kinetic molecular theory. Remember, you must have the kinetic molecular theory memorized for the test. First 4 points. First 4 points of the test. Flip the page. Some of this is just review. Here are the gas laws we just talked about. Boyle's law, Charles' law, Gay-Lussac, Avogadro's. Here's Maxwell Boltzman. I got cold gas, room temperature, hot gas. At the peak, that is your most probable speed, right? And then at the middle is going to be your average speed. Flip the page. Then we have our gases in our little jars. So the temperature of the first gas, and this didn't copy super well, is greater than the temperature of the second gas. How do you know on these 2 beakers? How do you know the temperature of this gas is faster than this gas? The little things. Can you guys see the little things? There's more on this one than this one. Yes? How do you know the mass is the same? They're the same size. So let's assume that they're the same size. It would be better if I could have printed this in color, but I couldn't. In this example, the mass is different, but the velocity is actually the same, because this one, if you count, it's 1, 2, 3, 4, and this one is also 1, 2, 3, 4. So which one of these would have a larger kinetic energy?
The bigger one.
The bigger ones, because Ke equals 0.5 mv squared. So just make a note that Ke, make that note, equals 0.5 mv squared. So V is the same, so this is going to only depend on mass. And we know that gas B has the larger mass. So here's my formula for calculating Ke. Here's my rate of effusion, molar mass 2 over molar mass 1. You can write it like this, or you can write it how I did it in the notes. You would agree that's the same thing, yes? However you guys want to do that is fine. I think it's easier to do the square root of molar mass 2 over the square root of molar mass 1, because usually you're solving for just one of those. But this will work too. It's just a little more simplifying if you're doing that. Then I've got a tube. If you put a cotton swab in one end of the tube, cotton swab on another end of the tube of 2 different gases, you eventually get a line that forms in the tube where the gases meet. It's kind of cool. So if I had, let's say I had NH3 on this side, and I had hydrogen on this side, where would that line form? Is it going to form closer to NH3, or is it going to form closer to H2?
I think the NH because it has a little minute.
NH3. So it's going to form closer to NH3, right? Because NH3 can't move as fast through the tube. Flip the page. So here we go. I have a sample of H2, HCl, and Cl2 at room temperature. Place the particles in order of decreasing average speed. So my fastest is H2. Why is H2 the fastest? What is H2's approximate mass? 2. Right? HCl's approximate mass is 36. And Cl2's approximate mass is 70. Right? So the more massive one is the slower one when we're talking about gases. Make sense? Okay, cool. So consider an equal molar mixture of gases H2N2F2 placed into a container with a pinhole. After some time has passed, place the gases of an order of increasing amount remaining in the temperature in the container. Try it. So least amount is first, most amount is last. So how would that look? This is that law of effusion. What would be the least? What would be the most remaining in that pinhole? So you have to think, what's the lightest? What's the smallest? What's going to get out more quickly than the other? We're ranking these. There's a pinhole. We're going to rank these of increasing amount remaining in the container. So the least amount remaining to the most amount remaining. So last night was the breast cancer awareness game for volleyball. So they decorated all of the railings on the bleachers. Did I tell you this? I told Coach. It looked like a bunch of peas, and we were playing Perry.
Are you serious?
Yes.
That's so fun.
It literally looked like we were decorating for Perry. It was even the shape of the Perry pea. I should have taken a picture of it. I didn't think of it. Least is going to be what? H2, because it's the lightest. The most has escaped. Middle is going to be N2. And the most left is going to be F2. Because F2 is what? Fat. Right? Think about it like that. It's going to be harder for F2 to escape through a pinhole. It's the heaviest. It cannot move very quickly. Kinetic molecular theory. More massive particles move slower. Less massive particles move faster. Okay, here we go. A 1 liter vessel containing 1 mole of H2 is shown below. Here's my lengths with the arrows. Draw the following. So on your own, draw the following. A vessel with 2 moles at 200, 1 mole at 200. And notice that these are changing. This is H2. This is Ne, H2, H2. So draw those. Make sure your number of molecules are the correct amount. So draw the correct number of molecules, the correct size of molecules, and the correct size of arrows for each one of those 4 scenarios. I'm having Taco Thursday for lunch today. The 8th grade teachers invited me, so. Are you guys done? Or are you still going?
How are we supposed to know how many are in one?
Well, 1 mole had only 3.
But then for neon.
Neon? We're assuming 1 mole is 3 particles. Let's just assume that 1 mole is 3 particles. We're assuming 1 mole is 3 particles. Just to keep it consistent. I guess I should say molecules, not necessarily particles, because there's 2 particles in a molecule of H2. I would say that the gas law test next Friday is much easier than the test we just took. So it should be a good first grade on the new 9 weeks.
What are we gonna do like the on this like lab that has like a lab report?
I don't know. Do we feel upset about not doing those? Really?
Wait, no.
You guys proved to me that you know how to write a lab report. All doing a lab report does is take more time of our class where I could be teaching, or more of your time when you could be doing practice.
We know how to write lab reports, we're good.
Maybe one more. I don't know.
I just don't think that's
Why'd you bring it up?
I'm just saying. I just don't.
Just wanted to know. And also, like, the AP test is not grading you on, can you write a lab report?
You just have to laugh.
We're shooting for 5s. This is what we're shooting for. We're not shooting for lab reports. That'd be impressive. I still can't believe that Megan got a 100%. What'd you get 100% on? A push. That's wild. That's wild. That's cool. Are you guys done? Okay. 2 moles at 200. How should my arrows look compared to this? About the same, right? So I'm not sure how you guys are going to draw that, but my arrows are kind of the same. What about B? A liter vessel containing 1 mole of Ne at 200. How do yours look?
That was.
Yes. Also, is neon a diatomic element? No. So these are bigger ones, still moving at about the same speed. A liter vessel containing 1 mole of H2 at 100 Kelvin. So I'm back to my little ones. And these arrows should be how compared to this? Tiny. Okay? Little tiny arrows. And then a 1 liter vessel containing 2 moles of H2 at 400 Kelvin. So I gotta have 6, 2, 3, 4, 5, 6. And these arrows should be how? Much faster, right? I like bouncing them off the walls. One tiny one though, just because. What if they would have said, like right here on A. Actually, let's go to C. What if they said a ½ liter vessel at the same temperature? And what would that done to my particle speed? Would the particles be moving faster? Would the speed of the particles be faster? No. Did my temperature change? No. Will my pressure go up though? Yes. Because if my particles are still moving the same speed, right? In a smaller space, what's there going to be more of? Collisions. Will. Less velocity? Well, we are assuming because it's 200 Kelvin that it should be about the same speed. We're just comparing to this. At 200 Kelvin, these would probably be moving slower compared to this, but we were just kind of comparing to the 200 here. You're right. In general, it's probably going to be a little slower, but we don't know exactly. Cool? Okay. Which sample, equimolar samples of N2 and O2 are both at standard conditions? By the way, this is not standard conditions. This is a mistake. This is STP. What are standard conditions? 298 Kelvin. So fix that. Which sample has more kinetic energy? It's the same. Yes. It is the same because the same temperature equals the same kinetic energy. Don't fall into that trap. They have the same energy. So if they're both at the same temperature, it's the same energy. Which sample has a higher average molecular speed though? N2. Why? It's smaller. It's smaller. Yes? Momentum? Not really. They're gas particles. They're so small. Your M for the MV is going to be so small.
So it doesn't really.
Nope. Okay. All right, place the following gases in order of increasing kinetic energy. This is kind of hard to see. Try your best, though. What? Cab? Yeah, that's right. C is less than A is less than B. It says increasing. Right? You guys okay with that? Okay. I got a Maxwell Boltzman distribution right here. What I'm going to do is I want you to draw these four of what it would look like. So if the gas is heated, how would it look? Higher molar mass at the same temperature, how would it look? Some gas removed, same temperature. A hotter gas was added and allowed to reach equilibrium. So draw those four new humps. Draw those four new humps. I'm going to see what day we are doing lab next week, because it might be Monday, and I want to make sure you guys know. I feel like Monday would kind of make sense. I don't know why this won't let me get out of full screen. That's so weird. Whoa. Second order. Oops. Here's the plan for next week. Monday, I'm giving you a day to work on problems from the book.
What?
That's a lot of problems, guys.
It is a lot of problems. Will we be able to ask you about them?
Yes.
It's pretty long.
Tuesday, lab. Wednesday, I will answer questions on the homework. Do you guys want to take the test on Thursday?
I think it would be helpful.
Yeah, because then we don't have to.
That's why we're gonna miss it that day
Yeah.
anyways.
Yeah,
Okay,
actually.
but I would rather have a review.
Wait, so then what would we do on Friday? But it's gonna be.
We need to keep the test Friday. Because I would rather have like a day to do like a review.
Well, I have to still review on Thursday.
So Thursday will be a review.
And what are we Wednesday?
Wednesday, wrap up problems.
Well, I have so it's like a whole week. I don't have a problem.
No, we have a lab Tuesday. Wednesday, I'll take some questions. I'll have like a maybe a review.
We could. What if we did like Wednesday, like we worked on the questions, and then Thursday. I mean, yeah, like Wednesday we work on the questions, and then Thursday we just go.
I'll probably do something like that.
If we've already done some of the questions, can you give us a review sheet on Wednesday,
I can do
and
that.
then we can work on the review sheet or the questions.
Yes. It's up to you. You can decide if you want to take it Thursday or. All right, how'd you guys draw this? Gas is heated. Your hump is going to be lower and to the right. Gas with a higher molar mass at the same temperature.
Mine is like the same proportion.
If it's a higher molar mass, that means it's going to be moving what? Slower. Therefore, my hump has to be higher and to the left. Think about that. Because it's the same temperature, higher molar mass, so the majority of them are going to be moving slower.
But then why on the other one did we keep the arrows so it's the same one between hydrogen and neon?
What are you talking about?
On like a couple problems ago, like you said that neon would have to.
Yeah, that's what we were talking about. Like, neon would probably have been a little bit slower.
Oh, okay.
It's not a perfect example. That's what Will was saying. Some gas removed, temperature held constant. How does this one look? It's going to be the same, but a smaller, huh? A hotter gas was added to the original container and allowed to reach equilibrium. I added some, and it's hotter.
A little bit farther, but
No, this has to be higher and to the right. Because I added gas, and it was hotter. I added gas, and it was hotter. What about 5? 2 gases at either end. Where is my circle going to appear in this tube? Somewhere like there. Because bromine is heavier. A sample of NO is placed in a sealed rigid container at 200 Kelvin. The vessel was heated to 400. What changes will occur and why? So, volume, what's going to happen? Nothing. Volume is going to be the same. Temperature. Temperature is going up. Pressure, what's going to happen to pressure? That's going to go up. Moles is going to be what? Same, because it's Y. It's sealed. Yes? What about particle speed? Particle speed is going to be higher. Boom! We finished. That is perfect timing.